Welcome to Design of Structure. In this lecture, we are going to start new lecture, new chapter, limit state of collapse for flexure member. In this chapter, we are going to study some basic data and the design of flexure member, also the analysis. In limit state design, a reinforced concrete structure is normally designed for limit state of collapse and is checked for limit state of serviceability. The collapse of structure occurs by failure of its member either in flexure, shear, bond, torsion, axial compression, or axial tension, or by combination of these actions. It is said that the structure is not failed monolithically, but it failed by a particular member. The other thing in mentioned is this paragraph are studied further in next chapters. Now the topic is theory of bending of reinforced concrete member at limit state of collapse. Extensive research carried out in the past several decades by engineers and scientists has established the ultimate strain theory of flexure of reinforced concrete members. On the basis of this study and finding of the research, the design code make the following basic assumption for the theory of bending of reinforced concrete member at collapse. Some basic assumptions are made for from the study and mentioned in IS 456 and respective Indian Standard Codes. Let us start now the assumptions. First assumption: a normal section plane before bending remain plane after bending right up to collapse. The ultimate state of collapse is said to have reached in flexure when the maximum compressive stress in concrete in the outermost fiber reach the ultimate reach the ultimate crushing strain. Higher code prescribe the maximum compressive strain in concrete equal to 0.0035, even though it varies with the grade of concrete between 0.0023 to 0.005. Next assumption is concrete under tension is ignored. It is said that concrete is weak in tension and strong in compression. So, while studying of reinforced concrete, we have to ignore the strength of concrete under tension, so that it is the one of the assumption for this. Tension is assumed to be carried entirely by reinforcement. So this is the another reason why we ignore the tension at concrete. The distribution of compressive stress in concrete across the section is defined by an idealized stress strain curve of concrete. Another assumption is perfect bond exists between steel and concrete right up to collapse. The design stress is steel reinforcement is obtained from the strain at reinforcement level using idealized stress strain curve for the types of reinforcement used. The word types of reinforcement used is very essential. Last assumption, but not in least, and it is not said last. There is a many more assumptions are there in IS code, but this is the last assumption for the flexural member is according to the IS code for the maximum strain in steel is tension shall not be less than 0.025 plus Fy divided by 1.15 into E S at collapse. The first assumption is well known Bernoulli's hypothesis. It means that strain at any point in a section is proportional to its distance xu. For the maximum stress, Fmax IS code adopt correction factor of 0.67 and partial safety factor of 1.5, giving design strength of the limit state of collapse, which is Fmax is equal to 0.67 FCK divided by 1.5 is equal to 0.446 FCK is all equal to 0.45 FCK, generally taken to describe the F maximum. The distribution of compressive stress across the depth XU of concrete in compression is often referred to the stress block since the strain diagram is linear over the depth XU. Skip all these steps because we study it in this diagram. This is the stress block parameter or stress diagram for con concrete reinforcement beam. This is the normal beam, cross section of beam, which depth is d. Small d is the depth of a beam from the top of the beam to the middle of the reinforcement, and the whole depth is considered is capital D. B is the width. Here, AST is the reinforcement area of reinforcement till NA is natural axis, which is passed through all these. This is the strain diagram. In exam, so it is said that stress strain diagram of a beam, in which we also saw that upper portion is about concrete and lower portion is about steel, compression member, tension member. So the design pattern of strain strain diagram is like this. Epsilon Cu and epsilon S, concrete and steel. The diagram is seems like similar, but it not. The upper body similar to the top, and the lower body of is similar to the depth of small d, not capital D, as I mentioned. XU, the terms I explain in few minutes. This is the diagram XU. This is a perfect natural axis concrete steel reinforced concrete structure in which the ratio of concrete and steel are perfect. Maximum ordinate of stress block K3 FCK is equal to Fmax area of stress block K1 FCK XU FAV into XU distance of the centroid or stress block from compression phase K2 into XU where XU is equal to depth of natural axis below the compressive phase, depth of concrete in compression or depth of stress block. K1 is equal to average compressive stress in concrete divided by cube crushing strength of concrete. which is FAV is equal to K1 into FCK. Same as K2 is equal to distance of center of stress block from compression phase divided by depth of stress block SU. Distance of centroid of stress block from compression phase K2 into XU, and the third K3 is maximum ordinate of stress block Fmax divided by FCK, which are cube crushing strength of concrete. So Fmax is equal to K3 into Fc. As seen in this section, K3 is equal to 0.446, the value of other stress block parameter. Thus, the depth of parabolic part of the stress block is equal to 0.002 divided by 0.0035 raised to mu is equal to 4 HU divided by 7. It is not raised to HU, it's about HU. The depth of rectangle part is equal to HU minus 4 HU divided by 7 is equal to 3 HU divided by 7. Trace blocks across a beam section. For above figure, area of trace block OABCDO. 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 Same as OABCDO. From the trace O, A, B, C, D and return to O. Area is equal to area of rectangular ABCD. It is divided into two parts as we done in mechanics of solid, and the other area of OAD for parabola. A is equal to 0.446 f dash ck into 3 by 7 into XU. We already considered it, plus 0.446 fck into 4 by 7 into XU into 2 by 3. 0.361 into FCK XU is equal to 0.36 FCK into XU. We are not using any kind of above data for any exam purpose and any study, but for get this equation we have to exercise of about all this we are doing. In next, we are not going to describe any such kind of exercise to derive the equation, because the all equation are given in IS 456 with number 96, and we are take from all that equations and do our job. Same as average stage is about FAV is equal to 0.36 361 into Fy, and then FAV is equal to 0.36. Similarly, for X bar, which are 0.416 is equal to 0.42 into HU, which all equations are given in the IS code. So I am not going to describe any of these. Now, mode of failure. The maximum strain criteria has been accepted as a failure criteria for a reinforced concrete member under flexure, as it agrees well with the test results. Therefore, a reinforced concrete member is considered to have failure when the strain in concrete in the extreme compression fiber reaches its ultimate value, which is 0.0035, which already we know. When this maximum stress in concrete is reached, the actual strain in steel can be equal to its failure strain or more than the failure strain or less than the failure strain, depending on the relative proportion of steel and concrete. In designing of reinforced concrete structure, the proportion of reinforced steel and concrete is such that the structure is stand with the monolithically by lifetime. Thus, based on the percentage of steel in the section, there three failure modes occur: Y, balanced section, under-reinforced section, and overturning or over-reinforced section. Or it's also called a failure of vice versa. And the corresponding section are called balanced under and reinforced section, which I've already mentioned. In next chapter, we are going to describe and study about balanced section, over-reinforced section, and under-reinforced section.